In this example, we're going to combine the concepts of equilibrium and tensile stress. A 30 kilogram box is being raised by pulling on the ends of a nylon cord that goes over two 3-meter high poles that are 4 meters apart. So we have two poles that are 4 meters apart. The height of the poles is 3 meters. On the top of each pole we have a pulley, and we connect a cord through the pulleys to a box that has a mass of 30 kilograms. So we pull on these cords. If we pull on these cords, the mass is raised. Now, if the diameter of the nylon cord is 1.15 millimeters, and the ultimate strength of the nylon under tensile stress is 500 times 10 to the 6 newtons per meter squared, how high above the floor will the object be before the cord snaps? So we want to find a certain height h above the ground where our rope will snap. In other words, in the first step of the problem, we're essentially asked to calculate or use the ultimate strength of our nylon cord to calculate the highest possible tensile force that the cord could experience before it rips. So we want to calculate the maximum tensile force the cord can withstand right before our cord snaps, our cord fractures. So recall that ultimate strength of our nylon cord is equal to force divided by area, where the force is the maximum force that the cord could experience before it snaps. So we know what the ultimate strength is, and we know what the cross-sectional area is, because we know our diameter is given to be 1.15 millimeters. So if we bring the cross-sectional area to the left side of the equation, we can solve for the maximum force. So force maximum is equal to 500 times 10 to the 6 newtons per meter squared multiplied by the cross-sectional area of our cord. So we assume our cord is circular, so that means the cross-sectional area is pi times radius squared, and radius is simply 1.15 divided by 2 times 1,000. The 2 comes from the fact that we want to calculate radius from our diameter, and the 1,000 comes because we're converting from millimeters to meters. So we calculate this, we squared multiplied by pi and multiplied by the ultimate strength of our nylon cord, and we get an approximate maximum force of 520 newtons. In other words, if the tension in the cord exceeds this value, our cord will snap. So now we look in step 2. In step 2, we want to calculate all the forces acting at this point. So at this point, we have the force of gravity, m times g, that's pulling directly vertically downward along the y-axis. And we have two identical tensile forces, Ft, which points this way, and Ft, which points this way. Now, if we draw a dashed x-axis, we see that our angle theta and angle theta with respect to this axis is the same at each point. And that's because the distance from each respective pole to where the force of gravity is acting is exactly the same. In other words, this right triangle has identical bases. So, right before our cord snaps, we're making the assumption that our box is in equilibrium, and that means the sum of the forces acting on our box, on the object, along the y-axis is 0. So these two forces are both at an angle, and that means they each have a y component force. So that means we choose going downward to be positive and upward to be negative. So the sum of the forces acting on the object along the y-axis is equal to m times g minus, because we have two forces acting along our y-axis, we have 2 times Ft times sine of the angle theta, and the sum is equal to 0 because the object is at equilibrium. Now, Notice we can replace Ft with F maximum. In other words, we're trying to find the situation where our object, right before our object, the rope, will snap. So we plug in F max into Ft, and now in step 3 we can solve for the angle. If we find what the angle is, we can find what the height is, as we'll see in just a moment. So sine of the angle theta is equal to m times g divided by 2 times F max. We plug in our quantities. M is 30 kilograms, G is 9.8 meters per second, and F max is 520 newtons. And we get 0.2827. Now we take the inverse of the sine function of this quantity and we get an angle of approximately 16.42 degrees. So this angle corresponds to this angle in this triangle. So let's suppose that the height h is the maximum height right before our object snaps. So we can extend and draw an x-axis like so, and this angle theta of this right triangle is this angle that we just found. So we know that the base of this right triangle is 2 because this object is right in between this 4-meter mark. So we know what the base is, we know what the angle is, we can use the tangent trigonometric function to solve for this height of our right triangle. And then we know what the entire distance is. It's 3, and if we take 3 and subtract the height of the triangle, we can find what this distance is, what the h value is. So we take our tangent function, we take tangent of this angle and multiply it by this base 2, and we get x. The height of this triangle is 0.59 meters. And now we take the entire height, 3, and subtract our value of 0.59 meters, and we get 2.41 meters. So that means this quantity here, the height, right before our rope breaks, is 2.41 meters.